Long before continents drifted and mountains rose, Earth's surface was almost unrecognizable. A young hotter planet sat under a rigid shell of rock, its crust barely moving while volcanoes bled heat from the deep interior. There were no shifting plates, no long mountain chains, only a restless world trying to cool and find its modern rhythm. If you enjoy calm journeys into Earth's distant past, please like, subscribe and share, and tell us in the comments, what do you most want to know about our planet before plate tectonics began? Thank you for watching. Now let's begin. The young Earth orbits a young sun inside a solar system that is still settling down from its formation. The time is early in planetary history, only a short while after Earth first becomes a mostly solid world. Around it, other rocky planets and many smaller bodies follow paths that are still slowly adjusting to one another. The last large collisions grow less frequent, yet space is far from empty. Remnant planetesimals, which are small building blocks of planets, still cross Earth's orbit and sometimes strike its surface. Each impact delivers energy, rock, metal, and in some cases water and volatile material that can evaporate or later condense. The wider environment of the solar system is calmer than during the earliest violent phase, but it still adds heat and material to the planet and helps set the starting conditions for its long, solid history. The sun at this stage shines more faintly than it does in later ages. Its brightness is lower by a noticeable fraction, because the star is still changing as it slowly turns hydrogen into helium in its core. That lower output of energy means that without other factors, Earth's surface would be colder than it is in later times. Yet the planet is not simply a passive receiver of sunlight. It still holds a large amount of internal heat from the energy of formation, from the separation of its metallic core from its rocky mantle, and from the ongoing decay of radioactive elements. This heat moves outward through the interior and eventually escapes to space. In the process, it shapes volcanoes' hot regions in the mantle and the overall behavior of the outer rocky shell. Even before true mobile plates exist, the balance between incoming solar radiation and outgoing internal and surface heat is already central to how the planet evolves. Beyond Earth, the giant planets follow their wide orbits. Their gravity helps sculpt the distribution of comets and asteroids, and can perturb smaller bodies onto new paths. Occasionally, one of these bodies is steered toward the inner solar system and eventually reaches Earth. In this era, such impacts are less intense than the very earliest bombardment, but they are still an important part of the planet's history. When a large object enters the atmosphere and strikes the crust, the collision releases enormous energy. Rock can melt or even vaporize, parts of the atmosphere can briefly heat dust, and gas can spread around the globe and local or regional surfaces can be reset. Over long timescales, however, the frequency of such events falls, and intervals of relative quiet grow longer. These quiet intervals give space for long-lived crust early oceans and a more stable outer shell to persist. The path of Earth around the Sun is now fairly regular and close to its present distance, so the average amount of solar energy received over a year stays within a limited range. Small changes in orbit and in the tilt of the rotation axis can still alter how sunlight is distributed between latitudes and seasons, but these variations operate within boundaries set by gravity and the presence of other planets. The rotation of the planet itself is faster than in later eras because tidal interactions with the Moon have not yet slowed it to the modern rate. A shorter length of day means that any given point on the surface cycles between light and darkness more quickly. This rapid spin influences atmospheric circulation and the behavior of the early oceans that will soon become important. But at this stage, what matters is that the planet is a spinning sphere with a stable, repeating pattern of days and nights. Deep inside, the metallic core continues to grow and cool, and its motion relative to the surrounding mantle contributes to a global magnetic field. The details of when a strong, long-lasting magnetic field first appears remain uncertain, but many studies suggest that Earth already hosts some form of magnetic shielding in this general interval. A magnetic field guides charged particles from the Sun and from space-shaping radiation belts and helping protect the atmosphere from being stripped away over time. Without such shielding, and without a sufficient gravity field, light gases could escape more easily into space. With it, more of the atmosphere can persist, letting Earth hold on to volatile compounds such as water vapour and carbon dioxide that are important for climate and surface conditions. The Sun itself is an active star in this early stage. It can send out strong flares and bursts of energetic particles that wash across the inner solar system. When these streams reach Earth, they interact with the magnetic field and upper atmosphere. They can change the chemistry of some atmospheric layers and produce displays of light at high latitudes. At the surface, the effects are muted compared with the large energy flow from the interior and the constant input of ordinary sunlight, yet they remain a part of the total energy and particle environment that surrounds the planet. Over millions of years, this environment slowly becomes less intense as the Sun evolves and the rate of strong flares declines, but during the time before full plate tectonics, it is still more active than in many later periods. On larger scales, Earth is one planet among several rocky bodies that each follow their own tectonic and thermal paths. Some of these neighbours may never develop long-term mobile outer shells, while others lose internal heat more quickly or more slowly. This variety shows that the style of tectonics is not fixed by planetary size alone, but also depends on internal temperature, water content and heat loss to space. In this era, Earth's internal heat flow is high, yet its outer crust has cooled enough to form a more continuous solid shell. The planet therefore occupies an intermediate state much hotter inside than in later ages, yet already coated with stable rocks and basins where water can gather. The surrounding solar system provides impacts, radiation and gravitational interactions, but conditions are moving toward a phase in which processes driven from within the planet will play the leading role. A faint sun, a still warm interior and a slowly quieting impact environment together define the outer context for the world that exists before modern-style plate tectonics begins to organize the surface into distinct mobile plates. In the time after the last global magma, oceans have mostly solidified. Earth carries a thin but continuous rocky shell over a still very hot interior. The earlier molten state leaves behind a strong thermal contrast between the surface and the deep mantle, and this contrast drives the way the first long-lived crust forms and behaves. At the surface, the rocks cool by radiating heat into space, and by contact with any atmosphere and water that begin to gather. Below the mantle remains near or above the temperatures at which it begins to melt over large depths, meaning that parts of it are still partly molten and can generate magma whenever pressure and temperature conditions allow. The result is a planet that is no longer an exposed ocean of magma, yet is far from geologically quiet. New crust keeps being manufactured and reshaped as the hot interior continues to supply melt. The first stable crust is mainly mafic, meaning it is rich in iron and magnesium, and poor in silica compared with later continental rocks. Such material is dense, dark, and similar to what later becomes common in oceanic crust. It crystallizes from the cooling mantle and from the last stages of magma ocean solidification, and it may form a patchwork of thickened regions and thinner areas separated by large volcanic centers. In some places, repeated upwelling of hot mantle produces broad volcanic provinces that pile lava and intrusive rocks on top of earlier layers. In other regions, the crust is thinner, more stretched, or partly removed by impacts. Through time, however, more and more of the planet's surface becomes covered by this solid shell, and the intervals between global resurfacing events grow longer. As this early mafic shell thickens, small differences in composition and temperature begin to matter. Wear melts interact longer with the crust, or where water is present, more silica-rich magmas can form. When these magmas cool, they produce lighter, more buoyant rocks, similar to those that later make up continental crust. These patches of buoyant rock can rise relative to the denser surroundings and form high-standing regions that resist being pulled back down. Over many cycles of melting intrusion and volcanic activity, such buoyant domains can merge into small protocontinents that stand slightly higher than the surrounding lowlands and basins. The appearance of these protocontinents marks a change in how the surface behaves. Instead of being a nearly uniform mafic shell, the outer layer now consists of a mix of dense, relatively low-lying crust and lighter, thicker blocks that are able to float higher on the mantle. However, because the mantle temperature is still high and the crust is relatively thin and weak, these early continents do not yet move as coherent plates in the modern sense. Instead, the whole shell tends to deform as a unit when forces act on it. Large-scale warping, sagging, and broad uplift can occur over thousands of kilometers, but clear long-lived boundaries between sliding plates are not established. The state of the crust in this era can be described as a stagnant lid, which is a style where one continuous outer shell lies over convecting mantle. In such a regime, most of the heat from below escapes either by conduction through the crust or by localized volcanic and intrusive activity, not by the recycling of large slabs into the deep interior along continuous subduction zones. The rigid shell can still fail locally, with pieces breaking and foundering into the hotter mantle, where they may partially melt and be reincorporated into new magmas. But this recycling is irregular and patchy, rather than organized along global plate boundaries. Impacts during this time continue to modify the crust. When large bodies strike, they create basins, lift rings of broken rock, and can punch through the existing shell to tap hot material from the mantle. These events remove older surface rocks and replace them with impact melt sheets and volcanic products, further blending different generations of crust. Although the overall rate of major impacts decreases with time, their influence on the architecture of the outer shell remains significant, especially when the crust is thin and the rigid outer shell is not yet strong. Over tens and hundreds of millions of years, the balance between crust creation and crust destruction slowly shifts. At first, new crust is produced rapidly from abundant mantle melt, and older crust is often reworked or buried. With progressive cooling, the mantle produces somewhat less melt, and the outer shell thickens and strengthens. As the lid becomes more robust, it becomes easier for parts of it to survive for longer intervals without being completely recycled. Ancient blocks of crust can then serve as seeds for further growth, when new magmas underplate them from below or rise into them from below, adding material at their margins and bases. These processes likely contribute to the growth of larger and longer-lived protocontinental regions. The presence of a continuous outer shell also affects how relief develops at the surface. Without widely spaced plate boundaries, most deformation is distributed rather than narrowly focused. Uplifted regions form above zones of mantle, upwelling or thickened crust, while broad depressions and shallow basins appear where the shell sags under its own weight, or where cooler, denser mantle lies beneath. These relief contrasts guide the early pathways of runoff, and the locations where water ponds as soon as stable oceans and lakes become possible. Yet at this stage, the focus remains on the physical state of the crust itself. It acts as the interface between the deep interior and the forming hydrosphere and atmosphere, transmitting heat and material upwards and receiving water and sediments from above. Chemical exchanges between cooling rocks and the first surface waters begin, but the system is still dominated by internal heat and rock mechanics. The exact timing and detailed sequence of these transitions from global magma oceans to long-lived solid crust remain an area of active research because later tectonic and erosional processes erase much of the direct record. Geologists infer this history from the few surviving very old rocks, from comparisons with other rocky bodies, and from physical models of how hot planets cool. Within the bounds of present knowledge, however, it is clear that by the time modern-style plate tectonics is still in the future, Earth already carries a more or less global solid shell with variable thickness and composition built from repeated episodes of melting intrusion and volcanism on top of a still hot and convecting mantle. This shell is continuous enough to behave as a single lid, yet it is internally varied enough to host the first buoyant crustal blocks that will later be important when the surface begins to break into separate mobile regions. Deep within early Earth, heat moves outward from several main sources, and this movement controls how the planet cools and how its outer shell behaves before modern plate tectonics begins. Part of the heat is a remnant from the violent growth of the planet when countless collisions converted orbital energy into internal energy. Another part comes from the separation of the metallic core from the surrounding rocky mantle, a process that released gravitational energy as dense metal sank toward the center. A continuing contribution arises from the decay of radioactive elements that are naturally present in the mantle and crust. Together, these sources keep the interior much hotter than the surface for a very long time and sustain vigorous motion in the mantle. The mantle in this era is not a rigid solid, even though it is mostly not molten. Over long periods, it behaves as a very slow moving material that can flow, stretch and fold under the influence of buoyancy and gravity. Hotter mantle material tends to rise while cooler and denser material tends to sink. This pattern builds large convection cells that act as a deep heat engine. Where hot material wells upward, it can partially melt and feed volcanoes or underplate the crust. Where cooler material descends, it carries heat downward and helps transport chemical components back into the deep interior. Because the mantle starts from very high temperatures, after the magma ocean stage, these motions are strong, but the presence of a continuous outer shell at the surface means that the way heat escapes is different from what it will be when separate moving plates exist. Instead of heat being carried efficiently downward by long, coherent slabs that sink along subduction zones, most of the thermal energy leaves through conduction across the base of the outer shell and by localized volcanic and intrusive events. In this stagnant lid state, the outer shell insulates the planet. The rocks of the crust and uppermost mantle cool from above and slowly thicken while the deeper mantle cools more gradually. Over time, the temperature difference between the upper and lower mantle decreases, and the driving forces for convection slowly weaken. But during the long interval before modern plates, this process is far from complete. The planet remains hotter inside than it will be in later eras, and its style of mantle motion reflects this high heat flow. Rotation adds another layer to the whole planet behavior. Shortly after its formation, Earth spins faster than it does in later times, because tidal interactions with the Moon have not yet transferred as much rotational energy from the planet to the lunar orbit. A shorter day means that the Coriolis effect, which is a tendency for moving masses of air and water to deflect as they move over a rotating sphere, is somewhat stronger. This effect helps organize large-scale atmospheric circulation patterns once a stable atmosphere and ocean are in place. Fast rotation can also influence how the liquid outer core moves, which is important for the magnetic field that surrounds the planet. The length of day gradually increases as the Moon slowly moves farther away, and tidal friction converts rotational energy into heat. But during the pre-plate tectonic interval, the day remains shorter than in later geological periods. Deep at the center, the metallic core forms as iron-rich material, and other dense elements separate from silicate mantle and sink inward. The core is mostly liquid metal at this stage, although the exact timing of when a solid inner core appears is still under study. Motion, in this electrically conducting fluid driven by cooling and by compositional changes as the core evolves, can generate a magnetic field through a dynamo process. The details of this process are still being refined in models, and by comparing with paleomagnetic signals recorded in ancient rocks, but many lines of evidence suggest that Earth carries a magnetic field for much of its early history. A magnetic field has important consequences for whole planet conditions. Charged particles from the Sun and from distant cosmic sources are guided by the field and tend to spiral along its lines toward high latitudes. Some particles are trapped in radiation belts, while others enter the upper atmosphere and transfer energy there. Without a magnetic field, more of the atmosphere could be eroded by direct interaction with the solar wind, the stream of charged particles flowing from the Sun. With magnetic shielding, much of this erosion is reduced, so gases released by volcanoes and by surface and subsurface processes can accumulate more easily. The exact strength and stability of the early magnetic field remain uncertain, but even a modest field can slow atmospheric loss and help preserve water and other volatiles that are important for climate and surface processes. The whole planet heat budget is therefore tied not only to the deep interior, but also to the presence of an atmosphere that can help regulate surface temperatures. Greenhouse gases in the atmosphere trap some of the outgoing infrared radiation emitted by the surface, which keeps the lower atmosphere and surface warmer than they would be if the planet were airless. This is especially important under a sun that emits less energy than at present. The balance between incoming solar energy, outgoing long-wave radiation, and geothermal heat from the interior sets the overall temperature structure of the planet. While geothermal heat is usually a small part of the surface energy budget compared with sunlight in a very hot young planet, it can be relatively more significant than in later times, especially near areas of strong volcanic activity and in the deep ocean. As the interior cools, the rate at which heat is delivered to the base of the outer shell decreases and the crust gradually strengthens. Denser parts of the lower crust can begin to become gravitationally unstable, meaning they are heavy enough compared with the underlying mantle to start to sink. In a world with a stagnant lid, this sinking occurs in a limited and patchy way, forming drip-like structures rather than long continuous slabs. These drips can carry dense lower crust and some upper mantle into greater depths, where they may partially melt and contribute to new magmas. Such processes allow some chemical differentiation and recycling between surface and interior even before modern subduction zones appear. Over hundreds of millions of years, these exchanges alter the composition of both the crust and the upper mantle, and gradually build more complex layering within the planet. Another aspect of whole planet behavior is the way that heat flow varies across the surface. Regions above strong mantle upwellings may experience higher heat flow, more volcanism and thinner crust, while areas above downwellings may have lower heat flow, thicker crust, and higher standing regions. Because the outer shell has not yet broken into plates, these patterns are broad and diffuse rather than sharply focused, but they still define large-scale provinces. Such provinces can persist for long times, because the stagnant lid slows the rearrangement of the surface. This stability allows certain crustal blocks to survive, while others are more heavily reworked, and it sets up long-lived differences in elevation and lithosphere thickness that will matter when plate tectonics begins. Overall, the early Earth in this interval behaves as a planet with a strong internal heat engine, a still rapid rotation, and an evolving core-generated magnetic field, all operating beneath a continuous but heterogeneous outer shell. The style of heat loss through a stagnant lid combined with gradual cooling and slow growth of density, contrasts in the crust and upper mantle, guides the system toward a point where parts of the shell can eventually fail more deeply and more often. At that later stage, the movement of separate plates will become the main way the planet sheds its internal heat. But in the pre-plate tectonic world, the key features of vigorous mantle convection, a solid yet deformable lid, and a whole planet energy balance that keeps the surface warm enough for long-lived oceans, while the interior remains hot and active. As the early solid crust thickens and the interior continues to release heat, Earth's atmosphere settles into a more stable state that still differs strongly from the air of later ages. The gases surrounding the planet come mainly from volcanic outgassing, from the release of material that was once trapped in the mantle and crust, and from contributions by impacting bodies that carry volatile compounds. At this stage, there is very little free oxygen in the air. Instead, the major components are likely nitrogen, carbon dioxide, and water vapor, with smaller amounts of gases such as methane, hydrogen, sulfur-bearing species, and noble gases. The exact proportions vary with time and location, and many details remain uncertain, because direct records from this interval are scarce and often altered. Within these limits, however, scientists can outline a picture of a thick greenhouse-rich atmosphere that plays a central role in keeping the surface warm under a fainter sun. The sun delivers less energy to Earth in this early time than it does in later eras, yet geological evidence suggests that liquid water can exist on the surface for long periods. This combination gives rise to the problem often called the faint young sun paradox. The solution lies not in a hotter star but in an atmosphere that traps more heat. Greenhouse gases such as carbon dioxide, water vapor, and methane absorb some of the infrared radiation emitted by the surface and lower atmosphere and re-emit it in all directions, including back downward. This process reduces the rate at which the planet loses heat to space and raises the average surface temperature compared with an airless or low greenhouse world. In the pre-plate tectonic interval, volcanic activity is intense and widespread because the mantle is hot and mobile. Volcanoes release large quantities of carbon dioxide and water vapor, and they may also inject significant methane and sulfur species into the air. These emissions help maintain a high greenhouse effect. Over time, weathering of rocks and the burial of carbon-bearing minerals and sediments can draw carbon dioxide out of the atmosphere, but in a world without fully organized plate tectonics, the rates and patterns of these processes differ from those on a planet with large mountain belts and deep oceans along plate margins. Much of the exchange between air and rock takes place on smaller protocontinents, oceanic plateaus and basaltic plains that are built and renewed by local volcanic and intrusive activity. The pressure at the surface, which reflects the total mass of gas in the atmosphere, may be higher than it is in later times, though the exact value is still debated. A higher atmospheric pressure would allow more gas to participate in heat trapping, and would influence how winds blow and how waves behave on any existing bodies of water. However, even if the pressure is not greatly different from later values, a higher fraction of greenhouse gases can still give a warm climate. This warmth does not imply that conditions are uniform. Regional differences in altitude heat flow from the interior, and proximity to active volcanic centers produce variations in temperature, humidity, and air composition. Yet on average, the climate appears to be mild enough for long spans to avoid global and persistent glaciation. Clouds are another key part of the early atmosphere. Water vapor carried upward cools and condenses into tiny droplets or ice particles to form clouds, which can both reflect incoming sunlight and trap outgoing infrared radiation. The net effect depends on cloud type, altitude, and coverage. In the early Earth, cloud properties are influenced by the abundance of aerosols, which are tiny solid or liquid particles in the air. Volcanic eruptions inject ash and sulfur-bearing gases that can form aerosols, while impacts can loft dust and vapor into the atmosphere. Some of these particles provide surfaces on which cloud droplets can form. An atmosphere with active volcanism and occasional impacts is therefore likely to host complex cloud patterns that change over days to years, but on longer timescales, the overall energy balance remains stable enough to support long-lived oceans once they have formed. High in the atmosphere, intense ultraviolet radiation from the young sun interacts with gases. Without much oxygen and ozone, more ultraviolet light can reach the lower atmosphere and surface than in later periods. This radiation can break apart molecules such as water vapor and methane, leading to photochemical reactions, which are chemical changes driven by light that reshape the composition of the upper air. Hydrogen that escapes from broken water molecules can be lost to space while heavier components remain behind. Over very long times, this process can slowly dry a planet, but Earth's gravity and growing cold trap in the upper atmosphere help limit the loss. Photochemical reactions can also produce hazes, especially if methane levels are high relative to carbon dioxide. Such hazes could raise the albedo, which is the fraction of sunlight reflected back to space, and partially counteract the greenhouse warming. The balance between haze cooling and greenhouse heating is another factor that shapes the early climate, and it likely varies with time as volcanic output, solar activity, and internal processes change. Because the record is incomplete, scientists often use models to explore how different mixtures of gases and aerosols would behave. These studies suggest that a wide range of atmospheric states is compatible with warm surface temperatures, provided greenhouse gas levels are sufficiently large. The air close to the surface is in constant contact with rocks and with any standing or flowing water. Chemical reactions between carbon dioxide-rich air water and freshly erupted volcanic rocks can form carbonates and clays that lock carbon into solid minerals. On local scales, these reactions can change the color and texture of rocks, produce soils on stable surfaces, and slowly draw down atmospheric carbon dioxide. In the absence of large, high-standing continents with extensive weathering fronts, however, much of this exchange happens on smaller land areas and on the seafloor near volcanic structures. Later burial and metamorphism of these carbon-bearing rocks can return carbon dioxide to the atmosphere or to shallow reservoirs, but in the pre-plate tectonic world, many cycles are incomplete or operate on different timescales and pathways than in the present. The atmosphere is also closely tied to the hydrological cycle, which links evaporation, condensation, precipitation, and runoff. As soon as long-lived oceans exist, water at the surface evaporates into the air, forming water vapor. When moist air rises and cools, the vapor condenses into clouds and eventually returns to the surface as rain, or at higher latitudes and altitudes snow. In a climate without frequent global glaciations, most precipitation falls as rain. Rivers and sheet flows carry water and dissolved substances back toward basins and lowlands where the cycle repeats. Even in the absence of modern plate boundaries, this continuous cycling of water shapes the landscape, redistributes heat, and influences how gases move between the atmosphere, ocean, and crust. Air circulation in this early time is driven by the contrast between warm equatorial regions and cooler polar regions, by differences between land and ocean, and by the rotation of the planet. Rising warm air near the equator and sinking cooler air at higher latitudes set up large convection cells in the atmosphere, while the Coriolis effect, which is the deflection of moving air over a rotating sphere, helps divide these into zonal wind belts. Over the ocean, winds drive surface currents that transport heat and influence climate patterns, though the detailed configuration of currents depends on the shapes and positions of emerging protocontinents and plateaus. Storm systems form where warm and cool air masses meet, and they can deliver intense rainfall to certain regions. On the whole, the early atmosphere acts as a mediator between the interior and space. It receives gases from volcanoes, and from reactions at the surface, it loses material to space through escape processes, and it interacts with incoming solar radiation. Its greenhouse properties allow liquid water to persist despite a faint sun, while its clouds and aerosols help regulate how much sunlight reaches the ground. Although much remains uncertain about the exact mixture of gases and the precise surface pressure in this pre-plate tectonic interval, The broad outline points to a thick, dynamic, low-oxygen atmosphere that stabilizes global temperatures enough for oceans and weather systems to function over very long timescales, setting the stage for the next layer of the system, which is the behavior of the global oceans themselves in a world without organized mobile plates. Once the atmosphere can sustain liquid water at the surface for long intervals, Earth's global oceans begin to take on a more steady character, even though the details of their extent and chemistry continue to change with time. Water that originally arrives in part from the mantle and in part from impacting bodies condenses as the surface cools and collects in low areas of the crust. Because the early crust is dominated by dense mafic rocks and large volcanic provinces, many basins form as broad depressions rather than narrow rifted margins. In a world without organized moving plates, these basins are controlled mainly by variations in crust thickness, thermal state, and impact structures so they can be long-lived and wide. Over time, much of the planet's surface becomes covered by interconnected bodies of water that together form a global ocean with scattered shallower regions above thickened crust and protocontinents. The temperature of these early oceans depends on the balance between greenhouse warming, incoming sunlight, and geothermal heat. Under a fainter sun, and with strong greenhouse gases, present models and geological clues point toward oceans that are on average liquid and stable, though they may be warmer than many modern seas. In some intervals, sea surface temperatures could be considerably higher than those typical of present tropical waters, especially near volcanic regions and in restricted basins with limited mixing. At depth, the oceans may be more uniform in temperature because there are fewer large continents and fewer strong density contrasts to drive complex circulation. Geothermal heat entering from the seafloor and from scattered hydrothermal systems helps maintain relatively warm deep water, while exchange with the atmosphere cools the surface layers. Without large polar ice sheets or frequent global glaciations, the contrast between equatorial and polar surface temperatures may be smaller than in some later periods, which in turn affects the strength of global currents. Chemically, these oceans are very different from modern ones. With little free oxygen in the atmosphere, most of the dissolved iron delivered from seafloor hydrothermal vents and from continental weathering remains in a reduced state and can accumulate in seawater. Sulfur-bearing species including sulfide are common, especially where volcanic gases and hydrothermal fluids mix with seawater. In many parts of the water column, conditions may be anoxic, meaning that dissolved oxygen levels are extremely low. In some deeper or restricted regions, the combination of low oxygen and high sulfide can lead to euxinic conditions, which are settings where hydrogen sulfide is abundant and can persist. These chemical states leave traces in certain sedimentary rocks and mineral deposits that form on or below the seafloor and are used by geologists to infer the nature of early oceans. Because modern-style plate tectonics with continuous subduction and organized mid-ocean ridges is not yet established, the seafloor behaves in a different way. New volcanic crust is created in broad regions above mantle upwellings and in large igneous provinces rather than along linear ridge systems. Once formed, this crust can remain on the surface for longer periods without being systematically recycled into the deep mantle along plate boundaries. As a result, large areas of basaltic seafloor can persist and interact with seawater through slow circulation in cracks and fractures. This interaction alters both the rocks and the ocean chemistry. Elements such as magnesium, calcium, sodium, and silica move between solid and liquid reservoirs, and the balance among them helps set the alkalinity, hardness, and buffering capacity of seawater. Over millions of years, precipitation of minerals from seawater, including carbonates and silica-rich deposits, builds sedimentary layers on the seafloor and on the flanks of protocontinents and plateaus. These sediments record the changing chemistry of the ocean and the balance between input from rivers' hydrothermal systems and atmospheric sources. In the absence of deeply incised continental margins and large deltas, many sedimentary environments are relatively shallow marine platforms, volcanic slopes, and impact-modified basins. Waves and currents rework loose material into sheets and banks, while finer particles settle in quieter waters farther from land. Organic matter from early microbial life, once it appears, contributes additional carbon and nutrients to the sediments. But in this pre-plate tectonic interval, complex life is not yet widespread, and much of the sediment is inorganic or microbially mediated rather than derived from large organisms. Circulation patterns in these oceans reflect the arrangement of land and sea, the rotation rate of the planet, and the strength of surface winds. With few large continents to disrupt flow, zonal currents can encircle much of the globe at certain latitudes. Warm surface water heated near the equator moves toward higher latitudes, while cooler water sinks and returns at depth. However, the structure of density in the water column controlled by temperature and salinity may differ markedly from modern conditions. High rates of evaporation in warm regions balanced by rainfall and runoff set surface salinity patterns, while hydrothermal fluxes at the seafloor add dissolved metals and other ions. Where basins are partially enclosed by protocontinents or volcanic plateaus, restricted exchange with the open ocean can produce strong stratification with stable, stagnant deep waters that are poor in oxygen. In more open parts of the ocean, winds and currents can mix the upper layers and bring nutrients from below closer to the surface. Sea level in this early time is controlled by the volume of water, the volume and density of the crust, and the thermal state of the lithosphere. A hotter mantle tends to produce thicker, more buoyant oceanic crust that stands higher, which can raise global sea level for a given amount of water. Large volcanic plateaus and broad upwellings further reduce the volume available for deep ocean basins. As a result, shallow seas may be widespread, covering large areas of low-lying crust. These epicontinental seas, which are seas that flood continental or plateau surfaces, can be broad and stable over long intervals in a stagnant lid world, because vertical motions of the crust are slow and diffuse. They provide extensive shallow water environments with abundant exchange between ocean and atmosphere, and between water and rock. Over time, slow subsidence of some basins due to cooling of the underlying mantle allows thicker sedimentary packages to accumulate, preserving longer records of ocean conditions. The absence of rapid, large-scale plate collisions and subductions means that these records are less frequently disrupted by mountain building and deep burial than they will be once modern plate tectonics starts. However, later tectonic and metamorphic events can still overprint or destroy parts of this archive, so the surviving record is patchy and must be interpreted with care. The interface between ocean and atmosphere in this era is a major zone of gas exchange. Carbon dioxide dissolves into surface waters and can be converted into bicarbonate and carbonate ions, which participate in the formation of carbonate minerals. Methane and other reduced gases emitted from hydrothermal systems or microbial communities can enter the atmosphere, where they are subject to photochemical breakdown. Nitrogen cycles between different forms, some of which are more soluble than others. These exchanges influence the long-term evolution of atmospheric composition and climate even before large continents and active plate margins appear. In turn, atmospheric pressure and composition control how easily gases enter and leave the ocean. Over long spans of time, the global ocean acts as a buffer, moderating changes in atmospheric gases by dissolving and storing them, or by precipitating them into minerals. In summary, the oceans of the pre-plate tectonic Earth form a connected dynamic system of warm to temperate waters, with low oxygen content, abundant dissolved metals and sulfur species, and circulation patterns shaped by a stagnant seafloor and modest topographic contrasts. They cover much of the planet lap against the margins of small protocontinents and plateaus, and interact intimately with the atmosphere above and the crust below. This oceanic layer transmits heat chemicals and eventually biological products across the globe, while the deeper interior continues to evolve toward conditions that will later allow the outer shell to reorganize into distinct moving plates. The solid outer shell of early Earth, which includes the crust and the uppermost mantle, begins to act as a distinct mechanical layer that carries stresses from both above and below. This layer, often called the lithosphere, is the part of the planet that responds in a mainly rigid way over long timescales, even though it can bend, crack, and slowly flow when stresses persist. Its development marks a key stage in the transition from a world dominated by short-lived magma oceans and impacts to a world where long-lived relief basins and protocontinents can persist before organized plates exist. The thickness of this outer shell is controlled by temperature. Near the hot surface and in the shallow subsurface, rocks can deform relatively easily over geological time. At greater depth, where temperatures are higher and rocks approach their melting point, they can no longer support strong, brittle stresses. The boundary between the colder, stronger layer and the hotter, weaker mantle below is not sharp but gradual, yet it is possible to define an effective lithospheric thickness, where deformation changes from mostly brittle or elastic to mostly ductile flow. In the pre-plate tectonic Earth, the mantle is hotter than it will be in later times, so this depth is shallower and the lithosphere is generally thinner and weaker. Over time, as heat escapes to space, the lithosphere slowly thickens, but during this interval it remains relatively fragile on geological scales. The composition of the lithosphere varies laterally. In some regions, it consists of dense, mafic crust, overlying mantle that has been only slightly modified from its original composition. In others, repeated melting and intrusion have produced more silica-rich rocks in the upper crust, which are lighter and more buoyant. These silica-rich patches can form the cores of protocontinents, while thick piles of basalt and related rocks form oceanic plateaus. Because the lithosphere carries both types of crust, its overall density and thickness vary from place to place. Thicker, more buoyant blocks stand higher, forming areas of relative elevation, while thinner, denser regions sit lower and are more likely to host deep water. At the scale of the entire planet, the lithosphere in this era behaves as a single lid that covers the convecting mantle. This stagnant lid does not yet break into large, long-lived plates that slide past and under one another along global boundaries. Instead, stresses from mantle convection from changes in load at the surface and from impacts are taken up by broad, warping, distributed faulting and localized foundering of dense material. When hot mantle rises beneath a region, it heats the base of the lithosphere and can cause it to thin by thermal expansion and by partial melting. This uplift can create high-standing areas or broad domes. When the mantle beneath a region cools and contracts, the overlying lithosphere can sag and thicken, forming basins. The result is a crust that shows gentle, wide-scale undulations in elevation, rather than sharp, concentrated mountain belts and trenches. Within the lithosphere, stresses accumulate as rocks are loaded and unloaded by volcanic constructions, sedimentation, or the growth and decay of ice and water loads, even if large ice sheets are rare in this warm climate. Thermal contraction as rocks cool also generates stress. When these stresses exceed the strength of the rock faults and fractures develop. In a stagnant lid world, such faults tend to be short and irregular compared with later plate boundaries, but they still provide pathways for magma to ascend and for fluids to circulate. Over time, repeated episodes of faulting intrusion and erosion create complex patterns of blocks and uplifts. In some regions, networks of extensional faults can stretch the crust enough to form local rifts and small seas even without fully developed plate margins. The lower part of the lithosphere can become compositionally distinct from the upper part through processes of melting and melt extraction. When mantle material below the crust partially melts, The residue that remains after melt is removed is often denser than the original rock. If enough melt is extracted, this dense residue can accumulate at the base of the lithosphere. As it cools, it may eventually become heavier than the underlying mantle and begin to drip downward. These downwellings remove dense material from the base of the lithosphere and can allow lighter material above to rise slightly, contributing to the buoyancy of protocontinental regions. Such gravitational adjustments, sometimes described as delamination or lower lithosphere foundering, are important ways for the lithosphere to evolve chemically and mechanically before continuous subduction zones appear. The thermal structure of the lithosphere is also crucial. Near the surface, temperature variations reflect climate topography and local heat flow from the interior. At depth, the main control is the balance between heat coming up from the mantle and heat conducted or carried away. Areas above mantle upwellings experience higher heat flow and a thinner thermal boundary layer, while areas above downwellings have lower heat flow and thicker lithosphere. In the early hot Earth, the average heat flow is high, so even the thickest lithosphere is not as thick as in many later periods. This means that the shell is more easily deformed and more strongly coupled to the underlying mantle motions. In such a setting, the difference between stable cratonic regions and more active belts is present, but less stark than in a cooler planet with deep, rigid roots under continents. Protocontinents that grow on this lithosphere are limited in size by the interplay of buoyancy, strength, and heat. As silica-rich crust thickens in one region, the base of the crust becomes hotter due to the insulating effect of the overlying rocks and the presence of heat producing radioactive elements. If it grows too thick, the lower levels can soften and partially melt, weakening the structure. This can lead to lateral flow of material spreading the protocontinent and preventing extreme thickness. The result is a set of moderate-sized blocks rather than vast high-standing continents. These blocks may cluster loosely because of mantle flow patterns and the tendency for buoyant material to collect, but they do not yet behave as parts of distinct mobile plates separated by continuous boundaries. Oceanic plateaus within the lithosphere are another important feature. They form where large volumes of basaltic magma erupt over relatively short geological intervals, often above mantle plumes or broad upwellings. These plateaus are thick, heavy piles of volcanic rock that can stand higher than surrounding seafloor simply because of their thickness, despite the density of their material. Their presence modifies how the lithosphere responds to loads and can redirect mantle flow beneath them, creating further variations in heat flow and stress. When they rise near or above sea level, they can host shallow marine or even subaerial environments, adding complexity to the interface between ocean and land. The mechanical behavior of the lithosphere in this era can be viewed as a balance between brittle failure in the upper parts and ductile flow in the lower parts. Near the surface, rocks break along faults and joints when stressed, forming blocks and fractures. At greater depth, rocks deform by slow creep folding and flow. The depth at which this transition occurs depends on temperature composition and strain rate, and it may be shallower beneath hot regions and deeper beneath cooler ones. Because the lithosphere is thinner and hotter overall than in later times, the ductile regime extends closer to the surface, which helps accommodate large-scale warping, but reduces the ability of the outer shell to maintain very steep high relief for long periods. The interaction between lithosphere and surface processes is continuous. As topography forms, gravity drives erosion and sediment transport downslope. Rivers and coastal processes cut into high-standing blocks and deliver sediments to basins. The removal of material from uplands and its deposition in lowlands changes the loads on the lithosphere, which can flex in response. This flexure can deepen basins, allowing more sediment to accumulate, and can cause uplift in surrounding areas. Even in a world without large organized plates, this feedback between erosion sedimentation and lithospheric flexure shapes the architecture of protocontinents and shallow seas. These adjustments occur slowly but steadily over tens of millions of years. Overall, the early lithosphere before modern plate tectonics is a continuous yet internally varied shell that transmits forces between the hot mantle and the cooling surface. It consists of thin, dense mafic regions and thicker, lighter protocontinental blocks of broad basins and gentle uplifts of oceanic plateaus and impact-modified terrains. Its mechanical state is governed by high internal temperatures, active mantle convection and ongoing magmatism, which together keep it relatively weak and responsive compared with the stiffer, thicker lithosphere of later times. In this framework, deformation is distributed, recycling is patchy and shallow, and the outer shell functions as a single evolving lid that sets the stage for how the deeper mantle will later begin to interact with the surface in a new way. Beneath the early lithosphere, the mantle moves in slow but persistent patterns that govern how heat leaves the deep interior in a world where the outer shell remains largely unbroken. The mantle is mostly solid rock, yet on long timescales it behaves like a very viscous fluid that can flow under the influence of buoyancy and gravity. Temperature differences, compositional contrasts and internal heating together drive convection, which is the movement of material that transports heat more efficiently than simple conduction. In this pre-plate tectonic interval, mantle temperatures are high, so the viscosity of the rock is lower than in many later periods, and convection is vigorous. Hot material rises from deeper levels, while cooler material near the base of the lithosphere tends to sink back into the interior, wherever it can find a path. Because the lithosphere is a continuous lid, the style of convection beneath it differs from that in a planet with mobile plates. Instead of narrow, well-defined down-going slabs that sink along extended plate boundaries, the cooler upper mantle may descend in broad sheet-like downwellings, or in more local drips where dense material at the base of the lithosphere becomes unstable. Upwelling regions can be wide and diffuse or focused into plume-like columns that carry hot material upward toward the underside of the lid. When such hot upwellings reach shallow depth, they may cause partial melting, feeding volcanic activity and underplating without necessarily breaking the surface shell into separate moving pieces. The depth structure of convection in this time is still a subject of active research. Some studies suggest that the mantle may be more mixed and less sharply layered than in later eras, because high temperatures enhance the ability of material to cross boundaries between upper and lower mantle. Other lines of evidence point to the possibility of partial layering with some chemical or thermal barriers that impede but do not entirely stop flow. Regardless of the exact pattern, the important feature is that large-scale circulation carries heat upward from deep within the planet, while cooled material near the lithosphere base returns downward, maintaining a long-term cycle. Internal heating from radioactive decay is distributed throughout much of the mantle, while heat also enters from the core below. The balance between heat produced inside the mantle and heat coming up from the core influences the geometry of convection. If internal heating dominates, rising regions may be broad and numerous, and downwellings may form where the lid cools and thickens. If core heat is strong, more focused plumes rising from near the core mantle boundary may play a larger role. In the early Earth, both sources are significant, and the mantle likely hosts a mixture of broad cells and narrower plumes. These features evolve slowly as the planet cools, but during the interval before organized plate tectonics they sustain high heat flow and frequent magmatism beneath a relatively thin outer shell. Chemical heterogeneity develops as melting and melt extraction change the composition of mantle domains. When part of the mantle partially melts, the melt separates and moves upward, leaving behind a residue that is depleted in certain elements. Over time, repeated episodes of melting above upwellings and plumes create regions of depleted mantle, while parts of the mantle that have received recycled crustal or lithospheric material may become enriched. In a stagnant lid, regime recycling of surface materials into the deeper mantle is less systematic than in a world with continuous subduction but it can still occur in limited ways. Dense lower crust or lithospheric mantle can detach and sink and impact events, or local foundering can transport material downward. These processes create a mantle whose composition varies with depth and location. Such variation affects melting behavior, because different compositions melt at different temperatures and pressures, and it influences how trace elements and isotopes are distributed, leaving signatures that can sometimes be detected in ancient rocks that survive at the surface. The flow field in the mantle also affects the shape of the planet over very long times. Where hot, buoyant mantle rises, the overlying lithosphere can be lifted, creating long, wavelength topography. Where cooler, denser mantle sinks, the surface can be depressed. These dynamic topography effects are subtle compared with local volcanic or impact structures, but can extend over thousands of kilometers and guide where basins and uplands develop. They interact with the mechanical properties of the lithosphere so that strong, thicker regions may transmit mantle signals over wider areas, while weaker, thinner regions may deform more easily and localize surface expressions. In the early hot Earth, with its relatively thin and weak lithosphere, mantle flow can more directly influence surface elevation and stress patterns than in many later times. Another aspect of deep mantle behavior in this era concerns the boundary at the top of the core. Here, heat flows from the hot metal core into the overlying silicate mantle. If the heat flux is high enough, it can trigger strong thermal boundary layers and vigorous plume generation. Rising plumes bring material that carries a record of core-adjacent conditions, including temperatures and chemical signatures altered by interaction with core-derived components. When such plumes reach the base of the lithosphere, they can cause extensive melting over broad areas, building large igneous provinces and thick volcanic plateaus. These events contribute significantly to crustal growth and modify the thermal and mechanical state of the lithosphere above them. In a stagnant lid planet, they may be among the most important drivers of surface change connected directly to the deep interior. Feedbacks between mantle convection and the outer shell evolve through time. As the mantle gradually cools, its viscosity increases, which tends to slow convection. At the same time, the lithosphere thickens and strengthens, making it more resistant to deformation. These changes reduce the efficiency with which the planet can lose heat through a stagnant lid regime. In response, stresses at the base and within the lithosphere can build up in certain regions, especially where density contrasts or thermal anomalies are strong. In some locations, this accumulation of stress may eventually lead to deeper, more continuous foundering of lithospheric fragments, and to the development of longer-lived downwellings that resemble early subduction zones, although these are not yet organized into a global network. Such transitions are gradual and may differ from place to place, but they mark steps along a continuum from purely stagnant lid behavior to a more mobile outer shell. Throughout this pre-plate tectonic interval, the mantle remains the main reservoir of heat and the main driver of slow planetary evolution. Its convection patterns, plume activity and chemical changes operate on timescales of tens to hundreds of millions of years, far longer than any human timescale, but central to the shaping of crust volcanism and topography. Above the oceans and atmosphere respond more quickly to changes in heat flow and volcanic output, but they are all ultimately linked to the slow circulation of rock deep below. The picture that emerges is of a planet whose interior is restless, even while its outer shell appears comparatively stable, a world in which convection beneath a stagnant lid steadily alters the conditions that will in time permit the surface to adopt a different style of tectonic organization. As mantle convection continues beneath the stagnant outer shell, certain regions of the crust begin to evolve into more buoyant, long-lived blocks that can be recognized as the first protocontinents, while other areas grow into thick oceanic plateaus. These features arise from the interplay of melting intrusion and density contrasts within the crust and upper mantle. In zones where hot mantle upwelling persists, repeated partial melting generates magmas with a range of compositions. Early pulses often produce basaltic lavas and intrusions that add mafic material to the crust. Later pulses, especially where water is present and where magmas interact with existing crust, can become more silica-rich. When these silica-rich melts cool and crystallize, they form rocks that are lighter than the surrounding mafic material. Over many cycles of melting and crystallization, these lighter rocks build up in the upper parts of the crust, while denser residues and cumulates tend to reside deeper. The result is a vertical separation of light and heavy material. Buoyant upper crust thickens and rises relative to its surroundings, while the dense lower crust may eventually become unstable and sink into the underlying mantle. This process of differentiation creates patches of crust that are both thicker and lighter on average than the neighbouring mafic shell. Such patches resist being submerged and can remain above sea level or in shallow water for long periods, even as the surrounding lithosphere flexes and deforms. These high-standing blocks are the seeds of protocontinents. They do not yet form large continents, but they stand out as irregular kernels of silica-rich crust, with their own local drainage systems, shallow shelves, and volcanic centres. The surfaces of these protocontinents are shaped by a balance between volcanic construction, intrusive growth, and erosion. Volcanic activity continues to supply lava flows and ash layers that blanket parts of the surface and create new relief. Intrusive bodies cool slowly at depth and add strength to the crust, forming cores of resistant rock. At the same time, rain rivers, coastal processes, and weathering gradually wear down elevated regions. In the absence of tall mountain belts driven by plate collisions, topographic contrasts on protocontinents may be moderate, but they are sufficient to direct water and sediment toward basins and shallow margins. Sediments derived from the erosion of volcanic and intrusive rocks accumulate along the flanks of protocontinents and in low areas within them, forming layered sequences of sand, silt, mud, and chemical precipitates. Over time, burial and mild metamorphism turn these sediments into sedimentary and metasedimentary rocks that record conditions at the surface. Because the crust beneath protocontinents is thicker and more buoyant than average, these regions tend to remain emergent or in relatively shallow water, providing stable platforms where extended sedimentary records can develop. Their stability is relative rather than absolute, as they still experience gentle warping, local faulting, and occasional volcanic or impact disturbances, but compared with the surrounding mafic basins, they are long-lived. Oceanic plateaus form in other parts of the lithosphere where mantle plumes or broad upwellings generate large volumes of basaltic magma over relatively short geological intervals. These magmas erupt onto the seafloor in repeated flows and intrude as sills and dikes into the existing crust. The accumulation of thick volcanic stacks raises the seafloor in these regions, creating broad, elevated areas that may approach or even reach sea level. Because the rocks are dense, the principal reason these plateaus stand high is their thickness rather than their composition. Their roots extend deep into the lithosphere, and their weight can locally depress the underlying mantle. The surfaces of oceanic plateaus host shallow marine environments when they lie below sea level, with carbonate platforms, volcanic islands, and shallow basins. When parts of them rise above the water, they develop sub-aerial volcanic landscapes and limited fluvial systems that deliver sediments to surrounding shelves. The transition from oceanic plateau to neighbouring deep basin can be gradual, with slopes covered by talus lavas and mass flow deposits. Together, protocontinents and oceanic plateaus introduce a new level of complexity to the surface of the pre-plate tectonic Earth. Instead of a simple world ocean overlying a relatively uniform mafic crust, the planet now displays a patchwork of thickened, buoyant regions and thinner lower-lying basins. This mosaic influences how oceans circulate, how sediments are distributed, and how heat escapes from the interior. Areas above thick crust generally have lower heat flow at the surface because the heat must cross a greater thickness of insulating rock, while areas above thin crust and strong mantle, upwelling show higher heat flow and more intense volcanism. The mechanical interaction between these thickened blocks and the surrounding lithosphere is subtle, but important. Protocontinents with their lighter composition and thicker crust are difficult to submerge, yet they are not completely rigid. They can tilt, warp, and break along faults when stresses build up, creating internal basins and uplifts. Oceanic plateaus, while mechanically strong because of their thickness, can also flex under their own weight and under loads from sediments and volcanic edifices. Where plateaus are adjacent to protocontinents or to other elevated regions, their combined loads and buoyancies can produce complex patterns of subsidence and uplift in neighbouring basins. In a stagnant lid regime, these interactions do not yet organise into long continuous margins with predictable relative motion, but they still structure the geography of the surface. Over long time scales, protocontinental fragments may cluster as mantle flow, and gravitational forces tend to bring buoyant blocks together. Where several such blocks approach one another, their intervening basins may become sites of thick sediment accumulation and magmatic activity. The crust in these zones can be strongly reworked by intrusions and by partial melting of older rocks, further increasing the silica content of some regions and deepening the contrast between light and dense crustal provinces. In this way, small protocontinents can gradually grow and merge into larger composite blocks, though this assembly is more diffuse and irregular than the later convergence of fully developed plates. Oceanic plateaus also evolve as they cool. Newly formed plateaus are hot and thermally expanded so they stand high. As time passes and the underlying mantle and plateau rocks lose heat, they contract and the plateau subsides. This subsidence allows new layers of sediment to accumulate over large areas, preserving records of changing ocean chemistry and biological activity once life becomes more widespread. In some cases, the cooling and thickening of plateau roots may make them more resistant to later deformation, turning them into strong elements within the lithosphere. In other cases, dense lower portions of plateau roots may become gravitationally unstable and detach, causing further subsidence and local changes in stress. The early emergence of these thickened blocks has consequences for the distribution of shallow marine habitats, for the pathways of weathering and erosion, and for the feedbacks between crust ocean and atmosphere. Higher standing protocontinents expose more rock to chemical weathering under the atmosphere, enhancing the conversion of carbon dioxide into dissolved ions and solid carbonates. Even though land areas are still modest in size compared with later supercontinents, their presence influences the carbon cycle and the supply of nutrients to the oceans. Oceanic plateaus, with their vast areas of basalt in contact with seawater, also participate in chemical exchange, taking up and releasing elements during hydrothermal alteration. In the context of a pre-plate tectonic Earth, protocontinents and oceanic plateaus therefore represent an intermediate step between an early planet with a mostly uniform mafic shell and a later planet with extensive continents and deep ocean basins separated by mobile plate boundaries. They create long-lived heterogeneity in thickness composition and elevation within the outer shell, while that shell still functions as a single lid over the convecting mantle. These features arise naturally from the physical properties of melting buoyancy and thermal contraction, and their gradual growth and interaction help prepare the lithosphere for the more focused deformation and deeper recycling that will come when the conditions for sustained organized plate boundaries are finally met in a later phase of Earth's history beyond the interval described here. The rigid outer shell of early Earth now works as a single planet wrapping layer that carries and redistributes stresses without yet breaking into a global mosaic of separately moving plates. This shell, which includes the crust and the uppermost part of the mantle, is cool and strong compared with the deeper interior, but it is still warmer and thinner than in many later periods. Its strength is enough to transmit forces over long distances, yet it is weak enough that those forces eventually lead to bending, faulting, and localized foundering when they exceed the capacity of the rocks to hold them. Beneath this shell, mantle convection continues to rise and sink in broad cells and plumes. Where hot upwellings push against the base of the lid, they tend to thin and lift it, creating gentle domes in the surface and raising heat flow. Where cooler mantle sinks, the shell sags slightly, forming broad depressions. Because the shell is continuous, these vertical motions are not confined to narrow zones, but are spread out over regions that can span hundreds to thousands of kilometers. The surface expression is a pattern of wide uplands and lowlands, with relatively modest slopes rather than sharply defined trenches, arcs, and ridges. Stresses in the shell arise from several sources that act together. Thermal contraction, as the planet cools, tends to pull the shell inward, creating tension that can promote fracturing. Loads from volcanic provinces, oceanic plateaus, and growing protocontinents press downward and flex the shell, producing bending moments that generate both tension and compression at different depths. Sediment accumulation in basins adds further weight, while erosion removes material from high areas and lightens them. Impacts from remaining asteroids and comets produce local craters, and basins shock the rocks and send seismic waves through the shell. Each of these processes leaves behind a pattern of stress that slowly relaxes but can combine with others to create zones of persistent weakness. Because the outer shell is not subdivided into plates, there are no long continuous boundaries where motion is concentrated. Instead, deformation occurs across belts and networks of faults that may run for hundreds of kilometers but usually do not circle the globe. In regions where the shell is stretched, normal faults open and the crust thins. These can form local rifts and narrow basins that fill with water and sediments, but the rifts often die out or are later overprinted by other events, instead of growing into mature ocean basins as they would in a later plate tectonic setting. In regions where compression dominates, thrust faults and folds develop, stacking slices of crust and thickening the shell locally. The resulting mountain belts are modest in height compared with later collisional ranges, partly because the lithosphere is relatively hot and weak, and partly because stresses are distributed rather than strongly focused. Shear stresses acting sideways across the shell cause strike-slip faults and zones of lateral displacement. These structures can offset earlier features and create complex patterns of fractured and rotated blocks, but again, they tend to be limited in length and do not form global systems of transform boundaries. The net effect is that the shell changes shape through a patchwork of overlapping deformational episodes, each linked to local and regional forces, rather than to rigid body motions of large plates. At depth within the shell, the lower lithosphere behaves more ductilely than the upper part. When dense material accumulates at its base, perhaps through the build-up of mafic residues, or the cooling and contraction of thick roots, it can start to sink into the softer mantle beneath. This sinking is not a steady linear descent like the motion of a mature subducting slab, but a more irregular process in which blobs and sheets detach and descend over time. As they peel away, the remaining lithosphere above becomes lighter and may rise slightly. This adjustment can reduce stresses in some areas while increasing them elsewhere. It also provides a limited pathway for surface and near-surface material to enter the deeper mantle even in the absence of continuous subduction zones. Such downwellings are most likely where crust is thick and has undergone extensive magmatic processing, such as beneath protocontinents and large igneous plateaus. The mechanical behavior of the outer shell is linked closely to its temperature structure. In hotter regions, the transition from brittle behavior to ductile flow occurs at shallower depths, so the shell is effectively thinner. Here, stresses are more likely to be relieved by slow-flowing deformation rather than by sudden brittle failure. In cooler regions, the brittle layer extends deeper, and faults can cut through a greater thickness of rock. This variation creates zones where earthquakes and rapid ruptures are more common, and zones where deformation is more gradual and distributed. However, because the absolute temperatures are still high, compared with later times, the shell as a whole is more deformable, and extreme long-lived topographic contrasts are harder to maintain. The absence of organized plate boundaries also changes how magmatism interacts with deformation. In a plate tectonic world, large volumes of magma are focused along mid-ocean ridges and volcanic arcs. In the pre-plate tectonic shell, magmatism is distributed more widely concentrated in regions above mantle, plumes, upwellings, and zones of local extension. Dikes and sills intrude along fractures that open in response to stress, and volcanic edifices grow where conduits reach the surface. This magmatic activity both responds to and modifies the stress field. Intrusions can strengthen parts of the crust by cooling into solid, coherent bodies, but they can also weaken it by introducing heat and fluids that promote ductile flow. Large volcanic plateaus add load and flex the shell, contributing to subsidence nearby. Over time, this interplay between stress magmatism and surface processes leads to a complex layered outer shell, in which old structures are partially preserved, partially reworked, and sometimes overprinted entirely. In some sectors of the shell, deformation belts may be reactivated repeatedly as mantle flow and surface loads change, creating long-lived zones of weakness that guide later activity. In others, ancient fabrics become locked in as the lithosphere cools and thickens, turning them into stable blocks. Yet even these relatively stable areas remain part of the single lid and do not yet drift independently over the mantle. Comparisons with other bodies in the solar system help illustrate this style. Some planets and moons appear to have spent much or all of their history in a stagnant lid regime, with large shield volcanoes, broad plains and deformation belts, but no clear evidence of long-term global scale plate recycling. The pre-plate tectonic Earth shares aspects of this behavior, though its higher internal heat, abundant water and dynamic atmosphere, and oceans give it its own distinctive patterns. These comparisons support the idea that a single rigid shell can host significant geological activity without breaking into plates. The key difference in Earth's case is that the internal conditions are slowly moving toward thresholds, where the shell may eventually become mechanically segmented. In this interval, the rigid outer shell without plates thus acts as both boundary and participant in planetary evolution. It limits the efficiency of heat loss by confining most recycling to shallow depths and localized drips, but it also records the signatures of mantle flow surface loading and internal differentiation in its warped and faulted structure. Its behavior is neither that of an unbroken, unchanging crust, nor that of a fully mobile plate system, but something in between, a flexible yet continuous lid whose internal variations in thickness, composition and strength set the groundwork for the later development of more focused, deeper-reaching tectonic processes when conditions in the mantle and crust continue to change beyond the time span considered here. As time passes on the pre-plate tectonic Earth, the planet's interior gradually loses heat, and this slow cooling reshapes the way the mantle and the outer shell interact. At the start of this interval, the mantle is extremely hot close to the temperatures at which large portions can partially melt. With such high temperatures, the mantle is relatively soft on geological timescales, and convection is vigorous. Hot material rises rapidly from deep levels, cools somewhat beneath the lithosphere, and returns downward in broad downwellings and localized drips. The rigid lid above is thin and weak, so it responds readily to the forces transmitted from below. As heat escapes into space through the surface and through the atmosphere, the temperature contrast between the deep mantle and the surface evolves. The mantle remains much hotter than the crust, but the average temperature in the upper mantle declines slowly. This change has several consequences. First, the viscosity of mantle rocks increases as they cool, meaning that their resistance to flow becomes greater. Convection cells still exist, but their velocities decrease, and the size and shape of upwellings and downwellings can shift. Second, the amount of melt that can be produced at a given depth and pressure decreases. Volcanic activity remains widespread, especially above plumes and upwellings, but the volume of magma generated per unit time tends to decline compared with earlier intense phases. Third, the base of the lithosphere gradually moves deeper, as the temperature at which rocks can deform brittly extends downward. The outer shell thickens and its effective strength increases, at least in regions where heat flow is average or low. The rate of interior heat loss depends on the balance between several processes. Conduction through the lithosphere is relatively slow but continuous. Wherever the outer shell is thick and cool, it behaves like a blanket, slowing the escape of heat from below. In contrast, volcanic eruptions, intrusions, and hydrothermal circulation provide more efficient channels in which heat is transported by moving material. In the early hot Earth, these channels are abundant, so the planet loses heat faster than it does later, when volcanic activity diminishes. Radioactive decay within the mantle and crust partly offsets this loss by producing new heat. But radioactive elements decrease over time as they transform into other species. Deep at the core mantle, boundary heat also flows from the hot metal core into the lower mantle, and that heat must be carried upward by convection. As the mantle cools, its style of convection adjusts to these changing input and output conditions. In some parts of the mantle, broad long-lived upwellings that once fed large volcanic provinces may weaken or break into smaller plumes. Downwellings may become more focused where dense lithospheric fragments have formed. Regions that are rich in heat-producing elements may stay hotter and more active for longer, while regions that are compositionally depleted may cool and stiffen sooner. This evolving pattern gradually increases the lateral contrasts in mantle temperature and viscosity. Above the mantle, the lithosphere responds to cooling in different ways depending on its composition and thickness. Under oceanic plateaus and mafic basins, the crust and upper mantle lose heat contract and become denser. This contraction can lead to regional subsidence, turning once shallow seas into deeper basins and allowing thicker sedimentary sequences to accumulate on top of the basaltic basement. Under protocontinents, which already contain more silica-rich, buoyant crust, cooling thickens the mechanical root and can increase the stability of these blocks. The base of the protocontinental lithosphere slowly moves deeper, forming a stronger, colder keel that behaves differently from the surrounding thinner shell. These keels can help preserve ancient crust against later deformation, even while the regions around them continue to evolve. Cooling also affects the density structure within the lithosphere and upper mantle. As rocks cool, they contract and become slightly denser. If a lower layer cools more than an overlying layer, its density contrast increases. Over time, parts of the lower crust or uppermost mantle that are compositionally dense and strongly cooled can become heavy enough to overcome the viscosity of the material beneath and start to sink. This process, often described as gravitational instability or foundering, can pull chunks of lithosphere into the deeper mantle. When such material detaches, it removes dense components from the base of the outer shell, making the remaining lithosphere above relatively lighter and more buoyant. The sinking fragments carry with them a record of surface and crustal composition into the interior, allowing limited recycling even before continuous subduction zones exist. Each foundering event alters the local temperature field because descending cool material chills the mantle it passes through, while rising hot material from neighbouring regions may move in to replace it. Over many cycles, these events contribute to a more complex pattern of temperature and composition within the mantle, with some volumes more depleted and cooler than others. The global rate of heat loss gradually decreases as the mantle cools and convection slows, but this decline is not perfectly smooth. Large magmatic events associated with strong plumes or with the opening of new basins can temporarily increase the rate at which heat and material reach the surface. After such events, the system relaxes again, and the overall trend toward lower heat flow resumes. The interplay between these episodic releases and the long-term cooling curve is one of the factors that control when and where the outer shell becomes more prone to deeper failure. As the mantle becomes more viscous, the forces it can transmit to the base of the lithosphere change in character. Convective stresses are still present, but the way they are distributed under the stagnant lid evolves. In some regions, the lid may become more firmly coupled to the mantle below, so that stresses build over wider areas rather than being relieved quickly. In other regions, where the lithosphere has become thicker and stronger, the shell may decouple partly from the underlying flow, riding more passively above it. Such decoupling can reduce deformation in some stable blocks, while concentrating it along their margins. Another consequence of gradual cooling is the changing conditions for melting at depth. With lower mantle temperatures, the depth range over which partial melting can produce voluminous magmas narrows. This tends to reduce the scale of new oceanic plateaus and massive igneous provinces compared with earlier times. In addition, with less widespread melting, the rate at which buoyant, silica-rich crust can be generated from mafic sources decreases. Protocontinents continue to grow, but their growth becomes more dependent on processes such as the remelting of older crust and the addition of smaller volumes of magma rather than on large pulses of mantle-derived melt. The thermal history of the interior is recorded imperfectly in the surviving rocks. Isotopic systems sensitive to cooling and radioactive decay capture some aspects of the temperature evolution, while the distribution of rock types and their metamorphic histories document changing patterns of crustal thickening, burial, and exhumation. In general, the record supports the view that early Earth is hotter and more strongly internally driven than later epochs, with a gradual shift toward cooler, more rigid conditions as time advances. From the perspective of the pre-plate tectonic world, this gradual cooling has two broad outcomes. It makes the lithosphere more capable of supporting long-lived strong contrasts in thickness and rigidity, and it changes the buoyancy and rheology of the crust and upper mantle in ways that can favour deeper sinking of some parts of the shell. When dense oceanic domains or thickened lower crustal roots cool enough, their tendency to descend into the mantle increases. At the same time, buoyant protocontinental keels become more resistant to such descent. These evolving contrasts in density and strength are necessary ingredients for any later transition from a stagnant lid regime to one in which segments of the lithosphere can begin to sink in more continuous paths, drawing the surface shell into a new tectonic mode. Within the interval described here, that transition is only being prepared by the slow work of cooling and differentiation. The planet remains in a stage where a single, mostly continuous outer shell overlies a convecting mantle that is gradually changing its character as its heat content declines. In the preplate tectonic Earth, one of the most striking expressions of the interaction between the hot mantle and the still continuous outer shell is the growth of vast volcanic plateaus and large igneous regions fed by focused upwellings that can be described as hot spots. A hotspot in this context is a long-lived region where hot mantle rises more intensely than in its surroundings, supplying a persistent source of magma to the base of the lithosphere. When such an upwelling first reaches shallow depth beneath a thin, weak lid, melting can be extensive. Large volumes of basaltic magma accumulate and then rise through fractures and conduits feeding simultaneous eruptions over wide areas. Instead of producing narrow volcanic chains, these events build broad provinces where thick stacks of lava flows and intrusive bodies spread across and into the existing crust. The resulting volcanic plateaus can cover hundreds of thousands of square kilometers and reach thicknesses of several kilometers. They form either on top of mafic seafloor or beneath relatively shallow oceans, and in some cases parts of them emerge above sea level. During the most active phases of such events, eruptions can proceed from many vents at once, with successive flows pouring out and cooling to form step-like layers of basalt. Between eruptive pulses, intrusive sheets and sills spread laterally within the crust, adding heat and strengthening some levels while weakening others. The weight of the accumulating lava and intrusions presses down on the lithosphere, causing it to flex. Near the center of the plateau, the crust may sag slightly under the load, while the region around the edges can be warped upward to form gentle peripheral uplifts. These flexural responses influence how sediments are later deposited where shallow seas form, and how fluids move through the newly created rocks. The thermal impact of large igneous regions is considerable. As hot magma intrudes and erupts, it transfers heat into the surrounding crust and into the overlying ocean or atmosphere. In the crust, this heat drives metamorphism and changes the physical properties of rocks within and beneath the plateau. Water and other volatiles circulating through fractures can react with hot basalt-altering minerals and releasing dissolved elements back into the ocean. Above sea level, thick lava fields can maintain elevated ground temperatures for long intervals as they slowly cool. This local warming is superimposed on the broader climate, which is set by greenhouse gases and solar radiation, and it can modify regional weather patterns. Large igneous events also represent major channels for volatile transfer from the interior to the surface environment. Basaltic magmas contain dissolved gases such as water vapor, carbon dioxide, sulfur-bearing species, and small amounts of other volatiles. When magma ascends and pressure decreases, these gases come out of solution and are released into the atmosphere or ocean. In intense eruptive episodes, the flux of gases can be much higher than the background level from ordinary volcanic activity. Carbon dioxide emissions from these provinces contribute to the greenhouse effect, while sulfur gases can form aerosols that reflect sunlight and temporarily cool the surface in some regions. In the ocean, hydrothermal systems associated with newly formed plateau crust circulate seawater through hot rock, changing both water chemistry and rock composition. These systems can enrich ocean water in metals and nutrients, alter its oxidation state, and build mineral deposits around vents. From the mechanical point of view, volcanic plateaus and large igneous provinces add thick, coherent blocks to the lithosphere. Their roots extend deep into the upper mantle, where dense mafic cumulates may accumulate at the base. Over time, as the plateau cools, this lower root becomes colder and can grow denser than the surrounding mantle. If the density contrast becomes large enough, parts of the root may detach and sink as described earlier, while the upper parts of the plateau remain buoyant. This process changes the stress and buoyancy structure of the lithosphere, locally promoting further deformation at plateau margins and influencing how mantle flow is deflected around or under these thickened regions. Not all hotspots produce the same style of plateau. In some cases, the upwelling is long-lived, but the melt supply is moderate, leading to chains of volcanic centers that build more modest swells rather than enormous flood basalt piles. These swells can still stand higher than surrounding crust, forming linear or radial ridges and shallow basins aligned with the direction of mantle flow. In other cases, the initial arrival of a hot mantle plume head may trigger a brief but extremely intense outpouring of basalt, creating a truly massive plateau, after which activity becomes more focused along narrow zones that can resemble early rifts or proto-plate margins. In a stagnant lid world, these patterns remain tied to the behavior of the mantle beneath a single continuous shell, rather than to the interactions of independent plates, yet they begin to introduce elements of localization and repetition in magmatic and deformational belts. The location of hotspots relative to existing protocontinents and earlier plateaus shapes the geological record that forms. When a plume rises beneath a mafic basin, most of the eruptive rocks accumulate underwater, and the resulting plateau builds up from the seafloor with flows piling on top of each other and intrusions threading the crust. When a plume encounters a protocontinent, magma can intrude into thick, more silica-rich crust, producing a mix of mafic and intermediate rocks, and causing widespread metamorphism. Parts of the protocontinent may be uplifted by the buoyancy of hot material and the pressure of intrusions, creating new highlands and deepening adjacent basins where sediments collect. Over millions of years, repeated magmatic episodes in the same general region can transform its structure, turning earlier crust into complex mosaics of intrusive volcanic and metamorphic rocks that together strengthen the core of a growing crustal block. The surfaces of volcanic plateaus experience their own evolution. Fresh basaltic flows are relatively smooth and hard, but as they cool and crack, they become broken into blocks and columns that can be worked by physical and chemical weathering. Where plateaus stand above sea level rain, and rivers carve channels and valleys, mobilizing debris that moves downslope and into surrounding basins. Along coasts, waves attack cliffs carved into basalt, producing beaches of volcanic sand and gravel. In shallow marine settings on plateau tops, carbonate-producing systems can develop once conditions permit adding new layers of sediment on top of the lava piles. Over time, as plateaus subside due to cooling and possible root loss, more and more of their surface falls below sea level, expanding the area of shallow seas. These changes feed back into the climate and ocean systems. The flux of dissolved ions from weathering basalt influences ocean alkalinity and the availability of elements such as calcium, magnesium, and iron. Extensive basalt weathering can draw down carbon dioxide from the atmosphere when carbonate minerals form, acting over long times to offset some of the greenhouse contributions of volcanic degassing. Hydrothermal alteration of newly formed crust creates additional sinks and sources for many elements, and the circulation of hot water through the plateau interior can continue long after surface eruptions cease, as long as there is a sufficient temperature difference between the crust and the ocean. Hotspots themselves are linked to mantle structure at depth. Some may be rooted in thermal boundary layers near the core mantle boundary, carrying material from very deep regions upward. Others may originate at shallower boundaries where composition or temperature changes create instabilities. In each case, the plume or upwelling maintains a column of warmer than average mantle that can persist for tens of millions of years. As the mantle gradually cools, the contrast between plume and background may change, altering the intensity of surface volcanism. Some hotspots may weaken or die out altogether, while new ones may form elsewhere. The shifting pattern of these upwellings means that the surface of the stagnant lid is repeatedly marked by volcanic construction in changing locations, contributing to the long-term reshaping of crust and lithosphere. Importantly, large igneous provinces and hotspot-related volcanism establish an efficient way for the planet to expel heat and volatiles from the interior, even in the absence of global subduction networks. They punctuate the slower background cooling with episodes of concentrated magmatic and tectonic activity. Each episode leaves behind thickened crust-modified lithosphere and altered ocean and atmosphere, and each adds to the heterogeneity of the outer shell. Over the long span of the pre-plate tectonic interval, these cumulative changes help set up the contrasts in thickness, composition, and strength that will later influence where and how the outer shell can break into more coherent segments when internal conditions evolve further. For now, in the period before organized plate tectonics, the world is one where large volcanic plateaus, sprawling flood basalts, and enduring hotspot swells act as major actors in the surface story, directly linking deep mantle processes with the shape chemistry and thermal state of the crust and oceans above. On the pre-plate tectonic Earth, the surface of the single outer shell is shaped not only by slow warping and volcanism, but also by the scars of impacts, and by the quiet, persistent activity of the early seafloor and its hydrothermal systems. Although the era of most intense bombardment has passed, sizable asteroids and comets still strike the planet from time to time, leaving basins and craters that modify the crust and interact with the oceans. When a large body enters the atmosphere, it compresses the air in front of it and sheds energy as heat and shock waves. If it reaches the surface intact, the collision releases kinetic energy that can melt and vaporize both the impactor and part of the crust. In a world with a relatively thin and hot lithosphere, the response of the crust to such an event is different from that in a cooler, thicker shell. The shock wave propagates through rocks that are already close to their thermal and mechanical limits, so fractures can extend deeply, and transient cavities can be large relative to crustal thickness. Immediately after impact, a central cavity opens, surrounded by uplifted rings and ejector blankets of broken material. In the seconds and minutes that follow, the cavity collapses inward, and the floor rebounds, creating complex craters and basins with central peaks or peak rings. If the impact occurs in a region covered by ocean, huge waves radiate outward, and water rushes into the newly formed basin, bringing sediments and dissolved chemicals from surrounding areas. If the impact happens on land or on a shallow plateau, debris and dust can be lofted high into the atmosphere before falling back to the surface where it mixes with local materials. Over longer periods, these impact structures become sites of focused geological activity rather than static scars. The fractures and faults created by the shock provide pathways for magma from below and fluids from above. In some basins, the crust beneath is thinned by the excavation, and mantle material is brought closer to the surface. Residual heat from the impact combined with higher than average heat flow from the underlying mantle can keep rocks at elevated temperatures for extended times. Magma may intrude into the fractured crust, forming dikes and sills, and in some cases volcanic eruptions can flood the basin floor, covering impact melt and breccias with sheets of lava. These volcanic infills smooth the topography and create new rock sequences that record both impact and magmatic processes. In ocean-covered regions, the newly formed basins quickly become part of the seafloor fabric. As water fills them, it begins to cool the hot rock, but circulation of seawater through fractures continues to tap residual heat. Hydrothermal systems develop as cold, seawater percolates downward heats up near hot rock, or magma reacts with the surrounding minerals and then rises back toward the seabed. The returning fluid is enriched in dissolved metals, silica and other components leached from the crust, and it may be depleted in or enriched in certain elements compared with the ambient seawater. Where these fluids emerge at the seafloor, they create vent fields with chimneys of precipitated minerals and steep chemical gradients. These hydrothermal areas are not limited to impact sites. Throughout the early seafloor, wherever there is fresh volcanic crust, strong geothermal gradients, and open fractures, seawater can circulate and form similar systems. Along the tops and flanks of large volcanic plateaus in zones of local extension, where the lithosphere is pulled apart and above mantle, upwellings that have melted the lower crust, hot basaltic rock, lies close to the ocean floor. The combination of high permeability in newly formed crust and strong temperature contrast between deep rock and cold seawater creates conditions in which convection cells of fluid can operate. Water descends through cracks, warms, reacts, and ascends again, carrying heat and dissolved material. The resulting vent fluids can emerge as hot metal, rich plumes that rise through the ocean, mix with surrounding water, and precipitate fine particles that fall back to the seafloor as layered deposits. Over time, these processes build mineral-rich mounds and crusts around vent orifices and create broader halos of altered rock within the crust. The chemical exchanges in hydrothermal systems play a significant role in controlling the composition of the early oceans. Metals such as iron, manganese, copper, and zinc are mobilized from the crust and transported into seawater. Some combine with sulfur to form sulfide minerals that precipitate near vents, forming ore-like accumulations and dark, fine-grained chimneys. Silica dissolves into the hot fluids and can precipitate as silica-rich layers or nodules when the fluids cool. Elements such as magnesium and calcium may be exchanged between seawater and rock, altering the relative proportions of these ions in the ocean. Hydrogen and reduced sulfur species can be produced by water-rock reactions affecting the redox state of local environments. In a low-oxygen ocean, these substances can accumulate to levels quite different from those seen in many modern vent zones. The seafloor itself, beyond the immediate surroundings of vents and impact basins, is a patchwork of flows, pillow lavas, and intrusive bodies that record ongoing magmatism in a stagnant lid setting. New basaltic crust forms above mantle upwellings and along zones of local extension spreading out in overlapping sheets. Because there are no long continuous ridge systems that feed seafloor spreading, as in a plate tectonic world, the pattern of seafloor ages and compositions is more irregular. Patches of relatively young crust can sit next to older regions that have cooled and subsided, and some areas remain unchanged for long intervals, because there is no organized subduction to recycle them. Sediments derive from distant protocontinents, from volcanic ash, from chemical precipitation, and from hydrothermal plume fallout, gradually bury large portions of the basaltic substrate building layered covers that thicken in basins and thin across uplifts. In some basins, especially those created or deepened by impacts, and later modified by mantle flow and lithospheric flexure, sediment thickness can reach substantial values even in the absence of plate margins. As these sediments accumulate, they compact under their own weight, slowly dewater and undergo early diagenesis, which is the suite of physical and chemical changes that turn loose sediments into solid rock. Pore fluids migrate along pressure gradients and can carry dissolved substances from one level to another, contributing to the redistribution of elements within the crust. At greater depths where temperatures are higher, some sedimentary layers experience low-grade metamorphism, developing new mineral assemblages that reflect the pressure and temperature conditions they have reached. In places where heat flow is particularly high or where magma intrudes nearby, metamorphism can be more intense, producing distinct belts of altered rock within and beneath basinal fills. Impact basins, early seafloor and hydrothermal systems together provide a variety of local environments that differ strongly from the average conditions of the planet. Impact sites offer steep transient gradients in temperature and pressure, followed by longer-lived zones of enhanced fracture permeability and magmatism. Seafloor away from direct impacts offers a background of slow cooling and sedimentation, punctuated by episodes of lava emplacement and intrusions. Hydrothermal fields create pockets of chemically rich fluids and altered rocks with strong contrast in temperature and composition over short distances. These environments are important not only for the cycling of heat and chemicals, but also for the physical evolution of the lithosphere. By altering rocks, hydrothermal systems change their density, strength, and ability to deform or fracture. Serpentinization of ultramafic rocks, which is the hydration of certain mantle minerals, can reduce density and produce hydrogen, influencing both mechanical behavior and chemical conditions. Deposition of minerals in fractures can seal some pathways while leaving others open, guiding future fluid flow and faulting. Impact-generated faults and breccias can remain zones of weakness that localize later deformation or magma ascent. Even though the shell remains formally continuous, These processes carve out internal boundaries and heterogeneities that shape how forces are transmitted and how the outer shell responds to deeper changes. The pre-plate tectonic seafloor, therefore, is not static or featureless. It undulates gently under the influence of mantle flow, carries thick volcanic plateaus and thinner basins, and is marked by impact structures and vent fields. It supports widespread hydrothermal circulation that couples the crust to the ocean and affects the chemistry of both. Over long spans, the cumulative effect of impacts magmatism, sedimentation, and hydrothermal alteration is to turn the outer few kilometers of the crust into a layered, chemically modified system that is different from the original basaltic shell. This dynamic interface between ocean and solid Earth, even in the absence of fully organized plate boundaries, quietly prepares the crust and upper mantle for deeper and more coherent recycling paths that lie beyond the time window considered here while remaining governed in this interval by the physics of a stagnant lid planet with a restless interior. The geological record that survives from the deep past of Earth is incomplete, yet it preserves crucial clues about what a pre-plate tectonic world looks like. Many of the oldest rocks reside in cratons, which are large stable blocks of crust that form the ancient cores of later continents. These cratons often contain rocks that are more than 3 billion years old, including both high-grade metamorphic terrains and belts of volcanic and sedimentary rocks known as greenstone belts. Within these ancient provinces, mineral assemblages, structures and chemical signatures together point to a style of tectonics that is more active than a completely rigid shell, but still different from the fully organized plate tectonics of later times. By examining these rocks, scientists reconstruct aspects of how the early lithosphere deforms how deep burial occurs, and how material cycles between surface and interior before long-lived continuous subduction zones dominate the picture. Cratonic interiors frequently expose high-grade metamorphic rocks that have been heated and compressed to conditions corresponding to deep crustal levels. These rocks, which include gneisses and granulites, record temperature and pressure histories that indicate thickening of the crust and prolonged residence at depth, followed by exhumation toward the surface. The mineral assemblages and chemical compositions of these rocks can be used to estimate the depths and temperatures they experienced. In many cases, peak conditions correspond to burial to tens of kilometers and temperatures of several hundred degrees Celsius. Such conditions are consistent with crustal thickening through horizontal shortening and stacking processes that resemble those in mountain belts, formed by plate convergence even if the global framework of rigid plates is not yet in place. The timescales over which heating, burial and exhumation occur can be constrained by isotopic dating of minerals that grow during metamorphism and cooling revealing cycles that last tens to hundreds of millions of years. Surrounding and intertwined with these high-grade terrains are greenstone belts, which are linear to irregular zones of volcanic and sedimentary rocks that have undergone varying degrees of metamorphism. The lower parts of many greenstone belts contain ultramafic and mafic volcanic rocks, such as komatiites and basalts, that point to high mantle temperatures and vigorous magmatism. Overlying layers include volcanic flows, volcanic lastics, and sediments derived from erosion of nearby highlands deposited in basins that may have been marine lacustrine or mixed. The structural architecture of greenstone belts often shows synclines and anticlines, thrust faults, and shear zones indicating that these sequences have been folded and faulted during multiple deformation events. In some regions, slices of different volcanic and sedimentary units are stacked on top of each other along thrusts resembling the imbricate structures seen in convergent margin settings. Such patterns suggest that even without fully developed plate boundaries, the early lithosphere experiences horizontal motions and compressive forces capable of constructing thickened crustal piles. The geochemistry of volcanic rocks in these belts adds further insight. Some suites display elemental and isotopic ratios that resemble those of modern island arcs or back arc basins, which on a plate tectonic planet form above subduction zones, where oceanic lithosphere sinks into the mantle. Other suites look more like intraplate basalts associated with mantle plumes. This diversity hints that multiple tectonic processes operate, including forms of subduction like recycling and plume-related upwelling, though the geometry and longevity of these systems may differ from modern ones. In particular, many Archean metamorphic belts show pressure-temperature paths that suggest relatively warm and shallow burial conditions, compared with the colder, deeper subduction that characterizes later eras. Rocks that have been subducted to great depths under low geothermal gradients in younger origins often show high-pressure mineral assemblages, whereas many ancient belts display evidence for high temperature at moderate pressures. This pattern is consistent with a hotter mantle and thinner lithosphere, in which any sinking slabs are warmer and more buoyant, limiting how deep they can descend before stalling or being reheated. Evidence for such shallow, short-lived subduction-like behavior comes not only from metamorphic conditions, but also from the distribution of rock types and structures. In some regions, narrow belts of mafic and ultramafic rocks lie adjacent to felsic to intermediate crust that appears to have formed through melting of older material. The juxtaposition of these units along shear zones and thrusts suggests that dense basaltic crust may have begun to dive beneath lighter blocks, triggering melting and magmatic addition in the overriding portions. However, the limited width and extent of these belts, along with the relatively warm thermal regime, indicate that these processes are not yet organized into extensive long-lived subduction zones, capable of recycling oceanic lithosphere on a global scale. Instead, they represent localized transient episodes where parts of the lid founder into the mantle and are reworked. Another line of evidence for pre-plate tectonic dynamics lies in the geochronology of cratons. Many ancient provinces show repeated pulses of magmatism deformation and metamorphism separated by quieter intervals. A craton can record a cluster of events around one time followed by relative stability, then another cluster several 100 million years later. Within each cluster, multiple rock types interact. Mafic intrusions cut earlier, crust sedimentary basins open and close, and metamorphism overprints older structures. This pattern points to episodic reorganization of the lithosphere, perhaps driven by changes in mantle, convection patterns, plume arrivals, or the gravitational foundering of previously thickened crust. Between these episodes, the crust can cool and stiffen, preserving the record of earlier processes. Such behavior contrasts with the more continuous global recycling that characterizes a mature plate tectonic planet, but is compatible with a world in which a stagnant or sluggish lid is occasionally disrupted by focused tectonomagmatic events. Cratons also preserve evidence of early continental weathering and sedimentation that reflect the existence of standing land and long-lived drainage systems. Ancient sedimentary sequences include sandstones, conglomerates, and shales that were deposited by rivers and along coastlines. Their compositions and sedimentary structures show that mechanical and chemical weathering has been operating on exposed rocks for extended periods. Paleosols, which are ancient soil horizons, occasionally appear in these sequences, indicating periods of surface stability on emergent land. The presence of such features demonstrates that protocontinents stand above sea level long enough to develop weathering mantles and to feed sediments into surrounding basins. These records, together with indicators of shallow marine environments on the flanks of cratonic blocks, support the view that buoyant crustal domains persist even while the underlying shell remains a single mechanical unit. Structural and metamorphic patterns within cratons and adjacent belts further suggest that deformation is often vertically integrated through much of the crust, rather than being restricted to narrow plate boundaries. Large-scale shear zones can cut through tens of kilometers of crust, accommodating lateral displacement of whole blocks relative to one another. These zones may be reactivated multiple times, recording changes in the stress field and in the direction of deformation. High-strain belts containing mylonites and other intensely deformed rocks mark regions where differential movement has been concentrated over long periods. The fact that such zones are widespread yet not obviously arranged into global networks of plate margins indicates that the outer shell deforms in a distributed manner. However, the repeated use of some structures hints at an emerging pattern of weakness that may later influence where plate boundaries will form when the system evolves toward greater mobility. Geophysical studies of present-day cratons which probe their deep structure using seismic waves and other methods reveal thick lithospheric roots extending well into the upper mantle. These roots are colder and more rigid than the surrounding mantle, and bear the imprint of early differentiation and cooling. Their thickness and chemical depletion suggest that they have been stabilized for very long periods, possibly since the Archean. Such deep keels are consistent with the idea that early tectonic processes including partial melting foundering of dense residues and limited shallow subduction-like motions have collectively left behind buoyant refractory lithosphere that resists later recycling. In a pre-plate tectonic framework, these keels represent regions where the outer shell has already developed strong internal contrasts in thickness and composition, setting the stage for later tectonic segmentation. Taken together, the evidence preserved in ancient cratons and greenstone belts portrays a planet that is neither entirely stagnant nor fully plate tectonic. The crust records thickening, burial, and exhumation, suggesting horizontal motions and vertical recycling. Volcanic and sedimentary sequences resemble in some respects those seen near modern convergent and intraplate settings, indicating a range of magmatic sources and tectonic environments. Yet the thermal regime is warmer, typical burial depths are shallower, and deformation is more distributed than in a planet governed by continuous global plate boundaries. These observations support a view of early Earth as a world with a single outer shell that deforms, thickens, and founders in places guided by mantle convection and internal density contrasts, while gradually building the strong, buoyant lithospheric cores that will eventually underlie larger continents when a more mobile tectonic mode emerges beyond the timescale considered here. As Earth's interior continues to cool and the outer shell becomes more differentiated, the conditions that control how the lithosphere can fail and sink begin to change in ways that move the planet closer to a new tectonic mode. Earlier in the pre-plate tectonic interval, the mantle is so hot and the lithosphere so thin and weak that any dense fragments that start to descend into the mantle tend to warm and lose their negative buoyancy before they can travel very far. Subduction, like processes where portions of the outer shell sink more deeply, remain shallow and short-lived. With time, however, the mantle temperature falls enough that the contrast in density between certain lithospheric components and the underlying mantle can grow larger, and the rheology, which is the way materials deform, shifts toward behaviors that can support more coherent sinking. One of the key factors in this evolution is the development of a more strongly layered lithosphere. Under oceanic domains, the crust is mostly basaltic and formed from mantle melts. As this crust cools and ages, it thickens, thermally becomes denser, and acquires a lower part that can transform into higher pressure mineral assemblages at depth. If water is present within the pores, fractures and minerals of this crust, some of it is carried downward as the crust subsides. At certain pressures and temperatures, basalt and related rocks can transform into denser assemblages such as eclogite, which is rich in high-pressure forms of pyroxene and garnet. This transformation increases the density of the lower crust and can strengthen its tendency to sink. Overlying this crust is the uppermost mantle portion of the lithosphere, which has been depleted by melt extraction and is therefore less dense than the underlying convecting mantle. The net buoyancy of an oceanic lithospheric column depends on the balance between the density increase in the transformed lower crust and the density decrease in the depleted upper mantle. As the planet cools and thermal contraction proceeds, the dense components grow more important relative to the buoyant ones, especially in regions where crust is thickened or where prolonged hydrothermal alteration and metamorphism have changed mineral fabrics. Water plays multiple roles in this transition. In the upper mantle, hydration of peridotite during processes such as serpentinization can reduce rock strength and lower the temperature at which ductile flow begins. Hydrated mantle near the base of the lithosphere is therefore weaker and more prone to deformation than dry mantle. In subcrustal levels, water present in minerals can be released during metamorphic reactions as rocks heat and are compressed. The liberated fluids can rise into overlying levels, reducing friction along faults and promoting melt generation. Fluid-assisted weakening of faults and shear zones makes it easier for parts of the lithosphere to slide relative to one another and for slabs that have begun to founder to continue their descent. At the same time, water influences the temperatures at which various minerals transform, which in turn affects density contrasts. These thermodynamic and mechanical effects combine so that portions of hydrated, cooled oceanic lithosphere can under suitable conditions become sufficiently dense and weak to sink more deeply than earlier drips and foundering blocks. Stress patterns within the outer shell also evolve as the mantle cools and as protocontinents and plateaus grow. Buoyant cretonic keels and composite blocks resist deformation more strongly than surrounding thinner lithosphere. Mantle flow tends to divert around these rigid keels, concentrating shear in the adjacent regions. At the margins of strong blocks, differential motion between the keel and the surrounding shell can localize strain into narrower belts. These belts may begin as broad shear zones, but can progressively focus into more discrete zones of weakness, as rocks within them are repeatedly deformed, fractured and altered by fluids. In some places, such zones may link up over long distances, approximating the kind of continuous boundaries that later characterize plate margins. Meanwhile, the accumulation of dense lower crust and mantle, lithosphere beneath basins, plateaus, and earlier thickened regions creates gravitational instabilities that can evolve from isolated drips into more connected downwellings. When portions of the dense root begin to sink, they can pull on the overlying lithosphere, bending it downward and generating extensional stresses in the trailing edge. This bending can open new fractures and faults that further weaken the lithosphere and facilitate the entry of water to depths where it can assist metamorphism and melting. If the sinking continues, a slab-like body of lithosphere can detach partway from the surface and descend at a steeper angle, drawing the trailing edge toward the zone of descent. In a fully developed plate tectonic system, this process becomes self-sustaining and produces continuous subduction zones. In the pre-plate tectonic interval, it likely occurs only in a limited episodic manner, and may stall or break apart before reaching great depths, but such behaviors mark a shift along a continuum from shallow drips to more slab-like sinking. The distribution of heat-producing elements also changes over time and space. Repeated melting and crust formation tend to concentrate radioactive elements, such as uranium, thorium, and potassium, into the continental crust, leaving the mantle more depleted. As protocontinents grow and stabilize, they become reservoirs of heat production near the surface. This concentration of heat influences the thermal structure of the lithosphere crust. Rich in heat producers can remain warmer at depth for longer, while underlying mantle cools. The resulting temperature gradients can alter viscosity and strength profiles, encouraging deformation in some levels, while stabilizing others. In particular, a relatively warm mid-crustal layer, overlain by cooler brittle rocks, and underlain by stronger mantle lithosphere, can act as a channel where horizontal flow and ductile shear concentrate. Such mid-crustal channels can decouple surface layers from deeper roots and allow differential motion that helps accommodate large-scale shortening or extension along evolving weakness zones. External factors such as the gradual brightening of the sun and the long-term evolution of the atmosphere and oceans also interact with these internal processes. As greenhouse gas levels change and the climate system responds erosion and weathering patterns on emergent landshift, enhanced chemical weathering of rising protocontinents under warm wet conditions can increase the rate at which mass is removed from uplands and deposited in basins. This redistribution of mass changes the loads on the lithosphere, prompting flexural responses that can elevate or deepen certain regions. Thick sedimentary piles that build in basins adjacent to strong blocks can weigh down the crust and contribute to its subsidence and subsurface metamorphism. In some scenarios, such sediment-loaded margins may become sites where dense lower crust develops, and later founders seeding new downwelling zones. Over very long timescales, these coupled processes bring Earth's lithosphere closer to a state where it contains strong, stable cores with deep keels surrounded by more deformable belts that host concentrated magmatism, metamorphism, and vertical motions. In those belts, the combination of cooled, dense oceanic domains, hydrated and weakened mantle, focused stress, and evolving fault networks makes it increasingly possible for portions of the outer shell to sink in a more coherent fashion. Yet within the interval considered here, the planet has not fully transitioned to a regime where such sinking is continuous along extensive boundaries, or where surface motions can be described as rigid plates sliding past and beneath one another over tens of millions of years. Instead, Earth resides in an intermediate state. The mantle is cooler and more viscous than in its earliest epochs, but still warmer and more vigorous than in later times. The lithosphere is thicker and more structured than the thin, fragile shell of the very early planet, but not yet segmented into fully independent plates. Episodic, regionally confined downwellings and shallow subduction-like events can occur, leaving metamorphic and structural traces in the rock record, but global recycling of oceanic lithosphere remains incomplete. The system therefore stands near a threshold with many of the necessary ingredients for mobile plate tectonics, emerging from the slow interplay of cooling differentiation, water transport, and stress focusing. While the outer shell still functions as a mostly continuous lid, whose internal contrasts hint at but do not yet express the organized plate behavior that will come later. In the late part of the pre-plate tectonic interval, Earth approaches a condition in which many of the separate processes that have been operating for hundreds of millions of years begin to align. The mantle is cooler than in earlier ages, yet still warm enough to sustain active convection. The lithosphere is thicker and more differentiated with strong buoyant cratonic keels, large composite protocontinents, and wide areas of oceanic lithosphere that have cooled, densified and accumulated chemically transformed lower crust. The atmosphere and oceans have long since settled into states that allow persistent liquid water and ongoing weathering. Together, these features create a planet where contrasts in buoyancy, strength and stress are sharper than before, and where the way in which the outer shell can respond to forces from within and above begins to show new possibilities. In the oceans, basaltic crust that has formed above upwellings and in extended regions now ages in place for long periods. As it cools, it contracts and subsides, increasing the depth of the seafloor and thickening the mechanical part of the lithosphere beneath it. In some regions, this crust carries a record of hydrothermal alteration and of chemical exchanges with seawater. Basalts and underlying mantle rocks hydrate along fractures, and some of the water is carried downward as the lithosphere sinks thermally. At depth, sections of the lower crust transform into denser mineral assemblages and become more prone to sinking relative to the hotter mantle below. where old oceanic domains are but buoyant cratonic blocks or thickened protocontinental margins, horizontal stresses transmitted through the single lid can concentrate. Contraction. As the planet cools, gravitational potential differences between high-standing keels and low basins and the drag of mantle flow beneath can combine to create compression at some of these boundaries and extension at others. In compression zones, the oceanic lithosphere adjacent to strong blocks may begin to flex downward, forming broad troughs that deepen with time. Sediments derived from nearby land and from distant volcanic sources accumulate in these depressions, adding load and further bending the lithosphere. As bending continues, the outermost part of the lithosphere experiences extensional stresses on the outer side of the developing flexure and compressional stresses on the inner side. Faults and fractures open above the outer rise while imbricate thrusts and folds develop closer to the strong margin. At a certain point, if the density contrast is large enough and the lithosphere has been sufficiently weakened by prior alteration, hydration and heating, the downflexed segment can become gravitationally unstable. It may begin to detach along a nascent shear zone and start to sink more coherently into the mantle. Initially, this descent is limited and may stall as the slab warms, but each such episode carries cooler, denser material, deeper than most earlier drips and foundering events. In places where this behavior repeats, or where the mantle flow pattern supports it, a more continuous pathway for sinking can be established resembling an early subduction zone. Above such a sinking slab, the overlying lithosphere can thicken and heat. Fluids released from metamorphosing rocks within the descending segment may rise into the mantle wedge above, lowering melting temperatures and generating magmas that travel upward. These magmas intrude the base of protocontinental crust or oceanic plateaus, and some reach the surface as volcanic arcs aligned roughly parallel to the zone of descent. The crustal rocks in the overriding region record renewed metamorphism, deformation, and magmatic addition-building belts that in some respects echo the patterns of later convergent margins. However, the thermal regime is still warm, so these belts are characterized by relatively high temperature, moderate pressure metamorphism, and by a tendency for slabs to remain shallower on average than in a mature plate tectonic system. Elsewhere, where the outer shell is under extension, rifts can open within the lid. Some rifts form inside large protocontinental areas, where gravitational potential energy stored in thick crust drives stretching. Others arise near the edges of strong keels, where the lithosphere thins as it flexes around their margins. In these rifts, normal faulting breaks the crust into blocks and basaltic magmas ascend along the fractures. If extension continues, these zones can widen into elongated basins floored by new volcanic crust. In a true plate tectonic world, such basins become the seeds of new oceanic domains and mid-ocean ridges. In the transitional pre-plate setting, many rifts remain confined and do not progress to full oceanic spreading, but a subset may approach the conditions needed for persistent upwelling and repeated intrusion along a narrow line hinting at the geometry of future ridge systems. The global arrangement of crustal blocks at this stage includes supercontinent-scale groupings of cratons and protocontinents as well as large oceanic basins. Within the supercontinent regions, thick lithospheric roots insulate the underlying mantle, encouraging hotter mantle flow around their margins. This flow can enhance upwelling and magmatism along some edges and promote downwelling and potential slab formation along others. The presence of such large buoyant blocks also affects how surface loads and dynamic topography are distributed, concentrating deformation into belts that surround or cut through them. Geological records from these belts show repeated cycles of basin opening magmatism, shortening and metamorphism consistent with an evolving system that is moving toward more organized, long-lived boundaries between domains. As these processes unfold, the average age distribution of oceanic lithosphere begins to narrow in regions where limited subduction like sinking has become recurrent. Their older, denser crust is more likely to be removed, while younger crust occupies higher standing parts of the seafloor. In contrast, in parts of the shell where sinking remains rare, very old seafloor can persist. This patchwork pattern of recycling by depth, dependent drips, short slabs, and incipient subduction segments produces a mantle that is increasingly structured by regions of downwelling and upwelling that are tied more tightly to the surface configuration than in earlier times. Chemical signatures in magmas recorded in surviving rocks from this later interval support the idea that recycled oceanic material and sediments have been carried to greater depths and returned in some form to the surface in arc-like magmatic suites. At the same time, the continuing presence of plume-related basalts and of intraplate-style volcanism indicates that deep mantle upwellings remain important. The coexistence of these different magma sources suggests a transitional tectonic regime in which both plume-driven and slab-influenced processes operate. From a whole planet perspective, the efficiency of heat loss through the lithosphere has increased compared with a purely stagnant lid. Regions with more persistent sinking and upwelling can transport heat more rapidly between deep mantle and surface, while stable cratonic keels act as insulating lids over parts of the mantle. The contrast between dynamic belts and rigid cores becomes sharper. Over very long timescales, this contrast encourages further focusing of deformation and recycling into the more mobile regions, reinforcing the emerging segmentation of the outer shell. Within the time frame considered here, however, Earth has not yet settled into a fully global network of organized plate boundaries. Some parts of the planet may behave in ways that closely resemble modern-style plate tectonics, with sustained subduction and arc magmatism, while others still follow a stagnant or sluggish lid pattern with only shallow recycling. The overall state is one of mixed and evolving tectonic styles tied together by an outer shell that is approaching but has not entirely reached a regime where distinct long-lived mobile plates dominate surface motions. The world at this stage stands near the threshold of that transformation, with its oceans, atmosphere, crust and mantle all bearing the marks of prolonged interaction under a mostly continuous lid that is beginning to fragment mechanically into segments whose eventual independent motion will define the modern plate tectonic Earth beyond the interval described here.